Hello everyone. Let's continue with the conclusion section of crosstalk. So in this scenario we saw that when your victim is weak, by weak I mean when the drive strength of the victim is low. In that case you see a glitch which is of a considerable height, and this particular glitch can result into functionality failures because this victim was at logic 1 and then eventually it moves to logic 0 and then it comes back to logic 1. So we don't know whether it will come back to logic 1 or it will come back to logic 0 or stay or remain at logic 1. So this particular thing is unpredictable. That's why a victim with a low drive strength creates a huge glitch. Again, a strong aggressor, an aggressor strong, by strong aggressor we mean the drive strength of the aggressor is very high. The resistance of the on transistor is very low. That's what we mean by a strong aggressor. In that case also, if you see the amount of charge that it can store for a very short period of time, that is very huge, and as a result of that you see a very high glitch at the victim side. This can also lead into functionality failures provided if it doesn't comes back to logic 0. If it stays at logic 1, the output of this inverter will be completely different, and that might result into some functionality failure. So this is another case where you see a functionality failure and a glitch which is very high, which is very dominant, and it's very unpredictable that what can go wrong because of this. Okay, this is one more example. So a low drive strength victim and a high drive strength aggressor is a big no-no for a crosstalk fix. This will result into crosstalk. So okay, this is one of the conclusions that we are making. Second, if you try to increase the victim strength, basically try to lower down the resistance of the on transistor of the victim, you might get a glitch which is very low, which is a bit lower than the previous one. So in this case also we have to decide what this particular, in this case it's definitely a failure because we have drawn that it will come back to 0, but it might not come back and stay at logic 1. In this case it might come down to zero voltage. There are other factors that it depends upon. For example, the glitch width also is one of the factors that it depends upon. We will be talking about that, and we have figures on and slides on those topic as well. But in this case there is a chance that the glitch might come down to 0 potential again. Oh, sorry, come back to one logic 1 over here because we have lowered down the resistance of this particular victim driver. So there is a slightest chance that it might come back to logic 1. Okay, that is one of the ways that you can reduce the crosstalk, basically increase the victim drive strength. Over here, if you reduce the aggressor drive strength, basically increase the resistance of the on transistor, you have the chances are that the amount of charge that it will store on the capacitor, that will be very less for a stipulated period of time. For this, basically we are talking a period of time from this point to this point. During this period, the amount of charge that this particular inverter can deposit on a capacitor is very low as compared to this one, because in this case it's like this is a very low resistance driver, this is a medium resistance driver. By medium resistance I mean the square boxes that we have drawn. The square boxes that we had drawn some time back, the size of the square box has been increased, has been reduced compared to this one. So as a result of that, the amount of current, the amount of charge that it will store on the victim on the victim capacitance or on the victim net will be a bit less compared to this one. As a result of that, the glitch height is still tolerable, and there is a slightest chance that it might come back to logic 0 voltage and avoid a potential functionality failure in the following circuit. Okay, so this is the second way, a second way to fix the glitch. It's like increase the drive strength of the victim or lower the drive strength of the aggressor. Okay, third point, and which seems to be the best one, is that increase the drive strength of the victim to a very high level. In that case, what will happen is the square box, the on resistance of this particular victim driver is very low. It is so low that immediately as it sees a loss in the charges over here, this particular victim driver will enable all these charges and bring it back to logic 1 voltage. What I mean is, whenever it's at logic 1, this particular victim net is at logic 1, and as soon as this victim driver sees a drop in the logic 1 voltage over here, what the victim driver does is it gets activated and it deposits the amount of charge that is required to bring the victim back to logic 1. So that's what the advantage that we see of having a victim driver, having a strong victim driver. On the contrary, over here, when you reduce the drive strength of the aggressor, in that case the amount of charge that the driver can deposit, or the amount of current that can get flown through this particular aggressor driver onto the victim net, will be very low, and as a result of that you see a very less amount of charge that gets deposited on the victim, and hence these glitches are avoidable. So this glitch and this glitch are kind of avoidable. So looking in all this scenario, looks like this is the best one that we have. This one is the best one that we have the best solution. But there is a small catch over here. So let's look into that catch. So we will look into the best possible solution over here, which is this one, where we have the victim very strong, and this actually helps to reduce the glitch on the victim net. But doesn't this seems to be similar to one of the diagrams that we have already drawn over here? Let's remove the other ones and let's look into the similar ones. So let's try to understand how are these two similar. So for few moments, just forget about the aggressor and the victim terminologies, and let's look into this from these two from a circuit point of view. So what we have is we have a driver, we have an inverter which is strong. Over here also we have an inverter which is strong. Over here we have one more inverter, nearby inverter, which is of a decent drive strength. We again have an inverter over here which is of a decent drive strength. We have a net which is connected to this inverter, and we have a net which is connected to this particular inverter, and we have a nearby net which is connected to this particular net. And same thing over here also, we have a net which is connected, or which is coupled to this particular nearby net. Okay, so the scenarios looks to be very same. So if the scenarios are same, the effect of the scenario will also remain the same. Now how is that? So if I try to remove this particular transitions and this particular glitches from this particular diagram, and just try to understand or try to analyze this circuit independently, irrespective of the aggressor victim terminologies and so on. So we had called this as victim, this as aggressor. Now let's remove those aggressor and the victim terminologies from this point, and let's try to analyze only this part with this particular scenario. So in this scenario, what we have is we have this particular strong victim. So when this victim turns on, or basically whenever this victim or the on transistor, the on PMOS transistor turns on, you have a flow of current, you have a flow of charges that makes this particular net to move from logic 0 to logic 1. Okay, and in this process, since this particular net is a nearby net, it throws some of the charges, or there is some amount of current flow that happens during this period of time onto the nearby net, and as a result of that you see a glitch over here, which is what we have learned so far. So now you see over here, this particular scenario and this particular scenario are exactly the same. And by exactly the same, I mean the amount of glitch that it produces and the amount of glitch that this particular scenario produces are exactly the same. Now what has gone wrong over here is the victim has now become the aggressor, and the aggressor has now become the victim over here. Okay, so making the victim, the victim, which initially this was the victim, by making the victim driver so strong, we have converted the victim to an aggressor, and we have converted the aggressor to a victim. So the most important conclusion that we need to make over here is, do not overfix crosstalk. When I say do not overfix crosstalk, I mean that do not increase the drive strength of victims so high that it itself becomes the aggressor, and all the nearby nets which is nearby to this particular victim net becomes the victims. So let me rephrase this again. Do not overfix or do not increase the victim drive strength so huge that its nearby net becomes the victims, and and the victim net becomes the aggressor. So this is the very important conclusion while fixing crosstalk. So we may end up with some more iterations of fixing crosstalk while if we try to do this particular scenario. The best way to fix crosstalk is, first, try to make the victim drive strength very similar to the aggressor drive strength. That could be very simple. That will reduce your glitch to a significant amount. And second, maybe first try to space this apart if there is routing resources available or routing space available, and then try to go for modifying the drive strength of victims or aggressor. So that would be one of the best approach. So what we'll do is, this is the very important conclusion that we have made over here, that we should not be overfixing things. So we should not be overfixing crosstalk. So that's what we'll leave this point over here, and next we'll move to what can go wrong if there is a glitch. It could be on the aggressor, it could be on the victim, it could be this scenario and this scenario as well. What can go wrong when you see a glitch, something like this? So what we'll do is, since I'm already running out of time, let's try to look into the effects of glitches in the next video. Thank you.